Inverting. Number 1, determine whether each of the following functions is invertible. If a function is invertible, find its inverse. On your calculator, graph both the function and its inverse to check that they are inverses. Part A, q of x equals square root of 2x plus 1. So it's probably difficult to know exactly what the graph of that looks like. I'm really hoping you know what the graph of square root of x looks like, and that you could know whether or not that's 1 to 1. But we could maybe graph this function and just double check that it's 1 to 1, meaning it passes the horizontal line test. So standard window is probably a good starting point. So that looks an awful lot like the square root function. Does it pass the horizontal line test? Yes, it does, because no horizontal line hits the graph more than once. So yes, it's invertible, which means we can follow that procedure we talked about during the lesson for this class. So let's go ahead and change the q of x to a y. Then let's interchange the x's and the y's. And then the heart of this problem is solving this equation for y. So we'll go ahead and square both sides. And then still solving for y, subtract 1. And then finally divide by 2. And then the last step here is to just replace that y with the symbol f inverse of x, except it's not f in this case, it's q. So q inverse of x is the function that we just found. Okay, so one small detail, and I'm not super interested in this detail, so don't sweat it, but technically, this function isn't the inverse as it sits. Let's take a look at the graph. It says we're supposed to graph both on the same set of axes. So we've already got the first one. So now we'll graph the other one, the x squared minus 1. Be careful with parentheses. Divide by 2. And we're expecting to see two functions that are symmetric about the line y equals x. Now to help us, let's go ahead and just graph the line y equals x here. If you have two functions that are inverses, then they're symmetric over that line, the y equals x. Flipping a point over the line y equals x, I should say reflecting it over that line, just is another way of swapping the x and y coordinates, and that's exactly what you do during this process here. So you swap the x and y right at this stage here. So hopefully that makes sense, that there should be symmetry over the line y equals x. But there's a problem. The original square root function comes in this way and then just stops right here. So it feels like the parabola, there's too much of it. It shouldn't have all of that. The only part that we should have, I think, is just this part here. I don't think we should have this part. If we wanted to have that part, then I guess this square root function needed to come down and flip over here. I think that this part that's missing would match up with this piece over here. So technically we need to say that this parabola function is only good for the points for certain points. And I think we need to cut out this. We need to cut out part of this parabola and just have a look at the other part. So how are we supposed to know exactly which parts of the parabola we should keep? Well, I guess we could zoom in. I need to figure out exactly where this parabola, I guess which part of the parabola corresponds to the starting point of the square root function, if that makes sense. So let's zoom in a little bit here. Maybe we can go 2's all the way around. And so this should give us a tighter picture of where the action is. So there's the square root function. Technically, it comes all the way down to here. There's just a little gap there, but that's not real. That's just a calculator issue. Okay, so I'm looking for just the parts that correspond to the square root function. So if I were to look at, for example, that x-intercept, which doesn't really appear, but it's there, and flip it over this line y equals x, I get to the y-intercept, which is right there. So it feels like the part of the parabola that I want is just the right-hand part, just from x equals 0 and then to the right. So that's one way to do it. Another way to do it is to recognize that let's see, it's one of these properties we just discussed in this class, that which one do I want here? The range of the original function is the domain of the inverse. So if you can look at this guy and figure out what the range of the square root function is, then you will know the domain of your inverse function. And the range of the square root function, well, it starts here on the y-axis and then goes up forever. So the range is all the y's bigger than or equal to 0, But now we're going to change the y to an x and say domain down here is all the x's bigger than or equal to 0. So however we get it, we technically should put in this little detail here. I'll put it in parentheses, x bigger than or equal to 0. And then I'll put not in parentheses, don't really worry about this. If you get it, super. If not, there are more important things to think about right now. Part B, f of x equals e to the minus x plus 1. It's a good exercise to maybe think about what the graph of this looks like without typing it into the calculator. That would be a good exercise in thinking about transformations of functions. But for right now, I'm just going to type it in. So if you haven't looked at it yet, maybe pause the video and then come back once you've given it a good shot to graph this one by hand. It's kind of complicated. Oh, I'm still zoomed in here, so let's zoom back out. So it's an exponential decay function, looks like that. Does it pass the horizontal line test? You bet. So that means we can go through the process and find the inverse. So we'll change the f of x to a y, interchange or swap the y's and x's. And now the hard part, solve for y. So the y right now is in the exponent. How do you bring the exponent down? You use logs. So you could use common log, but it makes more sense in this case to use ln. So we'll take ln of both sides. And then the nice thing is that ln and e cancel. They are inverses of each other. So the right-hand side is simply that exponent. Still trying to solve for y, so we can maybe subtract 1 from both sides. I'm going to put parentheses here. Let's try that again. Ln of x, subtract 1 from both sides. And then maybe multiply or divide both sides by -1. I'm just going to write this guy as 1 minus ln of x. Pause the video if that's not clear. Figure it out and then come back. And then the last step is instead of y, we're going to call it f inverse of x. So if we've done that right, then the graph here should give us, again, symmetry. So this one you should maybe try to predict what will the symmetric thing look like if we flip this guy over y equals x. So these points that are way up here, what happens? Let's see. I'll just make up some numbers. -2, 10. If I swap the x and y, 10, -2. 10, -2. So I'm expecting those points up there are going to go way out here and then maybe come up, come up, come up. And then these are points like, for example, 7, 0 essentially goes to 0, 7. So points that are very close to the x-axis become points close to the y-axis. So I'm expecting something that comes up here and then gets very close to the y-axis. So let's see if our intuition was right. 1 minus ln of x should be very close, and then coming out this way, so close that we can't even see it. If you were so inclined, you could zoom in and verify, but I think that it should do exactly what we expected it to do. Okay, moving on to part C. H of x equals x plus 2 over x plus 5. This one is quite similar to the example we worked in class. So first, let's take a look at this function. It's complicated, so we'll use technology to help us know what the graph of it looks like. Okay, that looks quite similar to the graph that we saw in class. Does it pass the horizontal line test? Yeah, it sure looks like it. There's no horizontal line that hits either this curve or this curve more than once. So we'll go through the process. It will be very similar to the one we did in class. Instead of h of x, we'll call it y. Interchange all of the x's and y's. Okay, so here's the hard part, is solving this new equation for y. We'll multiply both sides by y plus 5 to clear the fraction. There's y's in 2 places. Our technique is just like it was in class. We'll distribute and get all the y terms to one side and the non-y terms to the other side. So distribute the x. Get the y terms to the right and the non-y terms to the left by adding and subtracting as appropriate. And the whole point of that is so that you can factor out on the right-hand side. Both terms have y, so we can just pull out that y. And then finally solve for y by dividing both sides by 1 minus x. And that's our inverse function, so how about we give it the right name, which is h inverse of x. Okay, and we can graph this one. It's going to be kind of a mess on the calculator because the graph of the rational function here has the two different pieces plus the vertical asymptote. This guy will also have two pieces plus another vertical asymptote, but let's graph it and just see how it looks. Okay, it's going to be really hard to know what's happening here, but in theory, the one curve should be the mirror image over this diagonal line. Things look a little bit skewed. Maybe I should have done this at the start, but if we do zoom square, then that will square things up. The image looked kind of stretched just because physically this viewing window is a rectangle and not a square. So I think this will look a little bit nicer. Okay, so I can see some symmetry here in the curvy parts. This guy flips over y equals x and becomes this guy. That seems reasonable. And then this piece way out here flips over y equals x and goes very far to get way out here. Okay, so that seems okay. Part D. K of x equals x squared plus 2 over x squared plus 5. So this one, there's a problem, and you might have to graph it to see there's a problem, but maybe not. Maybe you can see there's a problem even before you graph it. And the problem is that this function, you can pick two different x's that give you the same y value. So if you haven't thought to do this, maybe do it now. Pause the video, come up with two different x's that maybe are going to give you the same y value, and come back when you're done. Okay, so the key here is that x squared, that's a giveaway. So if you were to pick a number like 7 and then plug in the same number but the opposite, then I can tell you you're going to get the same output. I don't even need to do the calculations here, but I do need to use the right letter. So let's use the right letter. This is the k function. And I can tell you it's going to be the same k of 7 and k of negative 7, because when you do 7 squared here and here, you're going to get 49. And when you do negative 7 squared, you will still get 49. And so the whole fraction will be exactly the same. And that makes this function not one-to-one and therefore not invertible. So there's nothing to do here. Now, even if you didn't see that just by looking at the x squared, that kind of that giveaway, if you've seen it before, you should hopefully see it from the graph. So if we graph x squared plus 2 over x squared plus 5, then we should see a function that is not one-to-one, a function where there's a horizontal line that hits it more than once. And okay, there's not a lot to look at here, but I can buy that there's a horizontal line that hits it more than once. In fact, I think there are a lot of them. Maybe we can tighten this window up a little bit. Let's try 0 to 2 on the y's. Stretched out, and we can see, oh yeah, there's plenty of horizontal lines that hit the graph more than once, so this function is not invertible. If you didn't do that, if you didn't see the x squared problem from the function rule, and if you didn't look at the graph to see the horizontal line problem, you could follow a process, right? You could go through this whole process. We accidentally got rid of some stuff here. This became x, and this was an equals. So you could go through the process, and as you go through the process, you're going to have to solve for y just like we've done. And when you do that, you're going to end up needing to take the square root of both sides. And when you take the square root of both sides, you got to put in that plus or minus. And that's the key, is that if this turned out right here to be plus or minus this thing, then it's not a function, right? Because there's the same one x value can give you two different y values, the plus or the minus. So that's the giveaway when you're actually doing the process. Even if you don't catch it because of the squared or because of the graph, you can still catch it at that moment. You have to put in the plus or minus. Okay, part E, same as D and same as C, but now it's an e to the x in the front. So it's not really clear what the graph of this looks like, but we can graph it here. Let's see, second e to the x. plus 2. Okay, I think that's good. And then the same thing here. Okay, so hopefully we've typed that in correctly. And then we can zoom 6, standard window. And let's see, does it look like it's 1-to-1? Well, I don't see anything going on yet. Okay, kind of hard to know exactly what's happening here. I guess we need to change our window. So maybe 0 to 2 is a good window for this one too. So that looks like a horizontal line. And if it is a horizontal line, then it is not 1-to-1. And then it grows. So this part right in here, no problem. And then it looks like it's getting horizontal again. But is it really horizontal, or is it just leveling off like an asymptote but never actually getting horizontal? So you can zoom in and play with the window, and I think you'll find that this is actually just an asymptote. It's never really horizontal. So this function is 1-to-1, and it does have an inverse, which we can find by going through the process. So instead of p of x, we'll call it y. Swap the x's and the y's. And then the tough part is to solve this for y. We will multiply both sides by the denominator to get rid of the fraction. It's kind of the same algebraic process up to a point. We'll distribute on the left-hand side. We'll group all the terms with y in it on the one side and everything without y in it on the other side. What are we doing here? Let's see. E to the y minus x e to the y. Okay, we cannot factor y out, unfortunately, but do not despair. We could factor something else out. What can we factor out on the right-hand side from both of those terms? We can factor out e to the y, and that's almost as good. Because we've accomplished the same thing. You had two different y's. How many do you have now? Just one. That's what factoring did for us. So let's divide both sides by 1 minus x, just like we did above. And then we just have one final step trying to solve for y. How do you undo e? We take ln. So ln of this stuff. And then we'll just change the y to the inverse notation. This is the p function, so p inverse of x. Okay, and we can graph this on the calculator. So we'd be expecting some mirror image of that. Some people find drawing mirror images to be very easy. A lot of people find it quite challenging. But let's see what the calculator does for us here. 5x minus 2 divided by 1 minus x. Okay, so is there anything that's going to look kind of like a mirror image? Well, that doesn't look good at all. Let's make sure I typed it in right. 5x minus 2 over 1 minus x. I think that looks good. Okay, so maybe we're zoomed in a little bit too much here. Let's see how we can change this window. Let's see, we were doing 0 to 2 here, so maybe we can go a little bit more. Let's try 0 to 10 on both. That's not what I meant. Let's try 0 to 10 on the y's. Let's see how this looks. Okay, so there's that function, and then we want to see some mirror image. Okay, this actually doesn't look too bad. This graph just mysteriously died, but it doesn't really do that. The calculator's having trouble graphing it. It grows so quickly here. There's a vertical asymptote at x equals 1. Okay, so what's going on here? Let's see. So there's that graph, and that part kind of looks like this part just flipped over, y equals x. So I guess what I need to see is that this piece somehow flips over y equals x, and I guess it should, let's see, close to the x-axis here, should end up close to the y-axis down here. So maybe the standard window is okay for looking at just that part. So I see this part here. I'm really hoping to see something similar to that down here.
Okay, I don't see it. It's hard to see, but this guy looks like it's kind of getting there. So I think that this is reasonable. I think we've got our function, and even though it doesn't look ideal, a lot of this is calculator issue. But I think that enough of it looks like it's flipped over y equals x that I'm feeling okay about that one. Move on to number 2. The function given by c equals t of f equals 5/9 f minus 32 gives the Celsius temperature C corresponding to a given Fahrenheit temperature F. Find a formula for T inverse of C. Okay, let's go through the process. So it says C equals this thing. I'm going to go ahead and now right away change the C's and the F's. Used to be swap the X's and the Y's, but now it's going to be swap the C's and the F's. So I'm ignoring this piece in the middle and just using the remaining equation, but swap C and F. And now it used to say solve the equation for y. Well, y is now being replaced with a c. So we're trying to solve this equation for c. So one thing you could do is distribute. I think it's probably better to move that 5/9 over right away. You could divide by 5/9. I think there's something better than that even. That's to multiply by 9/5. So let's multiply both sides by 9/5. And then solving for c by, we add 32 to both sides. Okay, and then good notation, this is really T inverse. Okay, so what's the x? Well, all right, so technically it should say T inverse of f. And as I think about it, I'm actually not thrilled with the directions to this problem, so I'm going to change it right now. But it says T inverse of C. I'm going to call it T inverse of f because it seems like that's the natural letter here. So that's my final answer, which disagrees with my answer key. So I'll put an or here. According to the directions, it should say C for some reason. So if you just change the F to a C, then you've got it, and this is the answer that's in the answer key. But I'm not as happy with that because that would seem to imply that the input for this function is a Celsius temperature, but I don't think that's right. I think the input is more naturally a Fahrenheit temperature. Let's see if I'm saying true things. And of course, I'm not saying true things. So let me retract and say that now that I think about it a little bit more, my answer key is something that makes me happy. So let's leave it in the answer key form and say that the input here is a Fahrenheit temperature. And so if we swap, if we interchange, then the input should be a Celsius temperature. So actually, this seems reasonable to me. The input of this function is a Celsius temperature. Okay, so hopefully that wasn't too confusing. I like the bottom answer, which matches the answer key. Part B, maybe we'll clear up a little bit of that confusion. Interpret the function T inverse. What are the units for its inputs and outputs? What does it represent? Okay, so for T inverse, the input is C, and the output, so the input is degrees Celsius, I guess I should say. Degrees Celsius. And the output is degrees Fahrenheit. I don't know how to spell that. And so how do we know that that's true? Well, take a look at the original function. In fact, maybe I should have thought of that before I wrote this stuff. So let's scratch that again. Sorry for that. If the video weren't so long at this point, I'd start over and make it again, but I've already spent 24 minutes and I ain't changing it even though it's not great. So let's go to the function t, the original function, t. So t has an input and t has an output. So let's fill in the original. So looking at the original function t, the input was in Fahrenheit, degrees Fahrenheit, and the output was degrees Celsius. That's what it says here. Gives the Celsius temperature, that's the output, corresponding to a given Fahrenheit temperature. So let's write that in here. The input is degrees Fahrenheit, and the output is degrees Celsius. So then when we go to the inverse function, we're just going to continue adding to our table here. T inverse, well, we know that the input and the output swap. The x and the y swap. The domain and the range swap. All of those are the same. So we're just going to swap. The new input is degrees
Celsius. And the new output is degrees Fahrenheit. And so then what does T inverse represent? Let's see, T inverse takes given temperature in Celsius, that's the input, and converts it to Fahrenheit, which is exactly the opposite of what the original function did. The original function, T, this guy, takes a given temperature in Fahrenheit, converts it to Celsius. The inverse function does the opposite. In red there, it says it takes a function in Celsius, converts it to Fahrenheit. Part C, the function given by n equals f of I equals 10 log of I over I naught gives the noise level n of a sound in decibels based on its intensity I. Whew. Part A, find a formula for f inverse of n. Okay, let's see if we can find our formula. Again, I'm going to ignore this little inner part for the time being. I have n equals 10 log of I over I naught. I'm going to swap the variables. It used to be x and y. The variables are now n and I. This is playing the role of x. This is playing the role of y. So we swap them. So the equation becomes I equals 10 log of n over I naught. I naught is just a constant. So I swap them. Now we solve for the new y. But remember, y is being played by n in this problem. So we solve for n. So let's solve for n. So n is right now buried quite deeply in this function. First thing we'll do is move the 10 over here by dividing. Okay, n is still buried. It's now inside of a log function. So how do you undo a log function? Well, you could hit both sides with a 10. You could take 10 and raise it to both sides. Or maybe more straightforward is you can just use the definition of the common log. There's an invisible base of 10 here. And maybe you remember the football play, 10 raised to this guy equals, cross the equal sign, equals whatever's in the parentheses here. So our new equation becomes 10 raised to the I over 10 equals the thing in the parentheses, and over I sub 0. And then still trying to solve for n, so multiply both sides by I sub 0. So that right there is our inverse function. Let's use good notation. I want f inverse of n, so we'll just change this guy to f inverse of n. So I naught times 10 to the I over 10 f inverse of, okay, at the moment it's actually f inverse of I, and I like the way I phrased the question now that I've thought about it a little bit more. So we're just going to change the i's right here and right here to n's, because that's a natural thing to do. We want f inverse of n. So then our final answer for this one, f inverse of n equals, the i's become n's, but I0 doesn't change, it's just a constant. This becomes n divided by 10. Okay, part B, interpret the function. What are the units for inputs and outputs, and what does it represent? So I think a good way to answer the input output function or question, and a good way to think about interpreting and what it represents, is to start with the original function and think about the input and the output. So the original function is f in this case, and f, what does it do? Let's see, it gives the noise level. So I'm now reading up here. This original function gives the noise level based on intensity. So it takes in the intensity and it outputs noise level. So let's write that. So the original function, the input is the intensity and the output is the noise level. If you feel like it, you can put some units on there. Intensity, what was intensity measured in? I forget, like watts per square meter maybe. And then the output is the noise level, that's in decibels. So then when we go to F inverse, what happens to the input and the output? Well, they swap. So the input of this function, the inverse function, is actually noise level. And the output is the intensity. So F inverse, F inverse gives, what does it give you when all is said and done? It gives the intensity for a given noise level. You tell me how many decibels the noise level is, and this F inverse function will tell me what the intensity of that sound is. Okay, so that red sentence doesn't need to be word for word, but you got to get the ideas across, and I think getting the ideas across is easier when you start with that table that we've written there in blue and black. Number 4, the function given by b equals f of t equals 1,000 times 1.06 to the t gives the balance b in a savings account earning 6% a year t years after it was opened with a $1,000 deposit. Part A, find a formula for f inverse of b. So let's try that. Again, I'm going to ignore this part here in the middle temporarily, and instead of changing x and y, we change b and t. So just interchange those two letters, swap them, and then solve for, okay, it used to be solve for y. What letter is playing the role of y in this problem? It's b, so we're going to solve this guy for b. Right now it's in an exponent. How do we handle variables in exponents? We use logs, but it's too early to use logs right now because there's 1,000 in the way. So divide both sides by 1,000, and then logs are the right tool. Okay, now we can use logs. You can use ln, you can use the common log, it makes no difference. I'll use ln in this problem. So ln of both sides. And then the nice property of ln that we're going to use here is that you can take an exponent inside of a log and bring it down to the front. So the left-hand side will copy, and the exponent comes to the front. I'll put a dot here to make it really clear it's multiplication, and then finally solve for b by dividing both sides by ln 1.06. Okay, so that's b, and then we want to finish this one up by using the good notation. So we'll do 2 steps in 1 here. So we're looking for f inverse of b. And so normally, well, I'll write it and then I'll erase it. So I would normally just say, okay, just copy the whole left-hand side. But this is that kind of funny business where it turns out the right thing to think about in here is b, not t. So we're going to change that t to a b. So I think that right there is our inverse function. And then moving on to part B, we're interpreting, and I'd encourage you to start with units. So let's start with units. And begin with f, and then we'll write it for f inverse. So what does f do? It gives the balance, that's the output, t years after the account was opened. So the input is time since the account was opened, and the output is the balance, how much money you actually have in your account. Given the time, this function outputs the balance. F inverse just swaps these two things. So given an input of a balance, F inverse outputs the time. What time? The time it takes to achieve such a balance. The F function in this case is maybe one that you've thought about a bunch. Tell me how long you have to wait, and this F function can tell you how much money you have in the account. But a different problem, an inverse problem, says, well, if I need to have a certain amount of money in my account, how long must I wait? And that's the problem that the F inverse function addresses. So F inverse let's see, takes in a balance and outputs how long you have to wait to achieve that balance. Those last three words seem very Zen-like to me. So again, your red sentence doesn't need to be exactly that, but has to get the right ideas across. I've tried to vary the way I've written this red sentence, just to give you a sense that there are different ways that the red sentence can be written. But again, you just got to convey the idea of input and output, and you want to try to write it kind of informally, not super mathematically speaking. You want to write it so that somebody not taking this class would have a good chance of understanding the sentence. Number 5. Function given by q equals f of t equals q naught e to the minus 0.0000121t gives the quantity q of carbon-14 remaining in an object after t years in terms of q0, the initial amount. A, find a formula for q inverse for f inverse of q. Okay, so again, we'll ignore this. Two variables here are q and t. That q naught is just a constant, so treat it as such. So we'll swap the q and the t. T equals q naught e to the minus 0.0000121q. Swapping t and q. And now solve this new equation for what is standing in for y. And the letter that's replacing y in this problem is q. So we're solving this equation for q. Q is buried in an exponent. Smells like logs, but you can't take logs yet because q0 is in the way. So divide both sides by q0 first. Still e to the. And now we can take logs. Would you use the common log or the natural log? It is much more natural to use the natural log here because there's e. So we just go ln of t over q naught. And then we know that ln and e cancel, and so we just get that exponent. And then the last step here is to divide both sides by the minus 0.0000121. Okay, and then we'll finish this one up with our good notation. So ln of t over q naught divided by negative 0.0000121. Instead of q, this one is better written as f inverse of q. But we're gonna make this small change here. It shouldn't be t in here. Q is the natural variable. So again, we'll just swap that out for q. Okay, part B is our standard question, and we'll begin with our standard way of writing inputs and outputs. And we'll begin with f, and we'll end with f inverse. Okay, so what's the input for the f function? It says up here, this function gives the quantity of carbon-14 remaining. So that's the output is the quantity of carbon-14 remaining after t years. So t years is the input, time is the input. So given a certain amount of time, this function outputs a quantity of carbon-14. I don't know chemistry. I don't know like chemically how they would write carbon-14. We'll just write C14. So F inverse, what does it do to input and output? It swaps them. Given a quantity of carbon-14, this function outputs the time it would take for the object to have that much carbon-14. So we'll write our sentence in red, try to change it up a little bit from the other red sentences. F inverse gives the time it takes to get to a certain level. Maybe I should say a certain quantity of carbon-14. Okay, when you're ready, next page. 6. Function given by h equals f of t equals negative 4.9 t squared plus 19.6 t for 0 less than or equal to t less than or equal to 4 gives the height h of a ball in meters t seconds after it was thrown upward with an initial velocity of 19.6 meters per second. A, explain why f is not invertible. Okay, so we mentioned this earlier, but a giveaway for a lack of invertibility is the squared. And oftentimes when you have something squared, you will be able to find two different values of the input that give the same value for the output. For example, you're looking for f of something to equal the same number as f of something else. It might not be obvious, like before I picked 7 and minus 7, and I don't think that would work in this case. But you're just looking around, so you can pick some numbers between 0 and 4 and just plug them into this function and see if you can find any two numbers that give you the same thing. But for example, if you happen to pick f of 1 and plug it in, and you also happen to pick f of 3 and plug it in, I think you'll get the same thing. So we can verify that, and we're going to end up graphing this function on the calculator anyway, so let's start there. Clear that temporarily. Okay, so we're typing in our function. And the standard window is probably not great here, but we can start there and then change it. Okay, so apparently the ball goes up and off the screen and then comes down. And it looks like it goes off the screen, or it starts here at 0, counting hash marks 1, 2, 3. It looks like it's back on the ground at 4. That makes sense. That seems to be the 0 to 4 domain that we were given here. So if 0 to 4 is the domain, then probably the middle is right there in the middle. The high point, I should say, is in the middle at 2. So I guess I'd really like to just plug 2 into that function and put that as my y max. Okay, so can we estimate that without writing too much out or without using the calculator? Let's see. That's about negative 5. Negative 5 times 2 squared. 2 squared is 4 times negative 5 is negative 20. That's about 20. 20 times 2 is 40. Negative 20 plus 40 is 20. So I'm going to guess that the max is up there right around 20. So let's change the y max to 20. Just for kicks, let's go ahead and change this guy to a 0. Okay, that looks pretty good. And then if we really want a nice window, how about we change it to 0 and 4 for the t values? And that seems like just about the tightest window we could find. It starts at the far left, ends at the far right, starts at the bottom, ends at the top. I think this is a great window. And if we were to find f of 1 and f of 3, I think we get the same number. So here's a nice little trick to finding f of 1. Hit trace and then 1. And enter, and it says 14.7. And then we'll do the same thing. Maybe we can just hit 3 now. Let's see, 3. Oh, we can. 14.7. And notice it puts the cursor right there at 3, 14.7. Whereas before when we hit 1 and enter, it was over here. So these guys are both equal to each other. Turns out they're equal to 14.7. So f is not invertible because we've got two different x's giving exactly the same y. Another way you could think about, or another reason this is not invertible from the picture anyway, is the horizontal line test, right? There's a horizontal line that hits the graph twice. We found this horizontal line up there. It hits the graph at 1 and also hits the graph at 3, but there are many horizontal lines that hit the graph twice. Or there is a horizontal line that hits the graph twice. This function fails the horizontal line test. Part B, restrict the domain of f so that it is invertible and find a formula for f inverse of h. And then there's a hint, but let's forget the hint for a second and just look at the graph again. So this function is not invertible. It goes up and that's no problem, but then as soon as it starts to come down, we've got this duplication of y values. The horizontal line test has failed. But the horizontal line test doesn't fail in here and doesn't fail until you start coming down. So if you decide to just stop the graph right there at 2, then I think that between 0 and 2, the horizontal line test is passed. And just as well, we could start the graph at 2, ignore this piece over here, and just start the graph at 2 and go to the right. So you could look at the graph just from 2 to 4. So I'm going to do that one just because it's probably a little less natural than the first one. Let's see. So then we could say, for example, that if you pick values of t between 2 and 4, then this function is in fact invertible. And you want to find formula for it. Okay, so let's go ahead and continue to ignore the hint, but cross this out and then swap the x and y, which is h and t in this case. So we go t equals negative 4.9h squared plus 19.6h. Now we're trying to solve this equation for h. Well, this is quite challenging, and in the video for the class, I said that oftentimes it's impossible to solve for y, solve for h in this case. But here, technically, it's just a quadratic equation where h is the variable. And we really like our quadratic equations to have 0 on one side, so let's put a 0 on the one side by subtracting t from both sides. And it looks kind of different than your usual quadratic equation, but this is a quadratic equation where h is the variable. Remember, quadratic equations have a's and b's and c's. So a is negative 4.9, no problem. B is 19.6, it's positive. C, it's kind of weird, but the constant term technically here is negative t. Even though it looks like negative t is a variable, we can treat it as a constant because we're trying to solve for h. Everything that's not h is just constant for us. Okay, so that means that you can go through the whole entirety of the beautiful quadratic formula using these values of a, b, and c. So let's try it down here. So this is now continuing into this space. Quadratic formula. Normally the formula says x equals, and then you guys know the rest. I'm just highlighting the x part because I need to change it. I need to know what it really is because there's no x in this problem. So what do we have playing the role of x? Is it t or is it h? Well, it's really tricky. But we're trying to solve this equation for h. And so normally this would be like x squared, and this would be x, and this would be some number. So the x is the thing that we're looking for. It's really h in this problem. So we get rid of the x, and we call it what it is, which is h. So when we use the quadratic formula, we're going to find h, which is exactly what we wanted, because if you think about what the goal is for this equation, it's to solve it for h, a letter that's like y. So let's go through the nitty-gritty details here. Negative b, negative 19.6 plus or minus square root of b squared, 19.6 squared minus 4 times a times the weird part, c, which is negative t, divided by 2a. Okay, so moving along here, let's see, negative 19.6 plus or minus square root of. Okay, so trying to square 19.6. And I'm actually looking at the answer key now because I'm a cheater like that, and it didn't even square 19.6. So let's use the calculator. Square it, and we'll get what the number is here. 19.6 squared. Okay, 384.16. Okay, and then 3 minus is still minus. 4 times 4.9 is at 19.6. Let's see if I got that right. Okay, that's good. And then divided by, don't forget, yeah, we got the t there, and then divided by negative 9.8. So that right there is h. Lovely. So then in terms of writing it with good notation, that's our inverse function. And this function was named f inverse. So I'm just running out of space, so I'm just gonna erase this guy. Well, maybe I'll leave it there and I'll put a line through it so there's still some record of it. We're replacing this guy with f inverse, and normally it's of x, but in this case we want it to be f inverse of h, which means that we're also putting a line through this guy and changing it to an h. Remember, all the variables kind of get swapped out at the end again. Okay, so it's kind of funny here because we've now got f inverse, but it's got a plus or a minus in it. And so that means it's actually not a function. It's got two different pieces in it. So it's still tricky, but we got to figure out which one we want. So let's think about our graph here. We were looking at the graph of this piece. I just chose to go from 2 to 4. So I need something that's going to correspond to this piece right here. It's either the plus piece or the minus piece. Okay, so let's do a little bit of work on the calculator. This is going to be messy, but we can handle it. So I'm just going to type in one of these pieces here. I'll type in the plus. Let's just see what that looks like. So very carefully typing in all of this stuff. Negative 19.6 plus square root 384.16 minus 19.6x, close the parentheses, divide by negative 9.8. Okay, I'm not exactly sure where the graph is going to be. I'll just hit graph and see if it's anywhere even on the screen. It's not, that's bad news. We'll double check that we typed it right. 384.16. We did not type it right, so let's fix that. It's these extra parentheses that I needed right here. That captures the top as one thing. So let's try this again and see if it's anywhere on the screen. Okay, there's something, not a lot, but something. Okay, so let's think about the graph of y equals x, because that's our kind of standard line for symmetry. So there's the y equals x lines. Okay, so now I've got a better sense. I need things to be flipped over that line. And let's think about the window a little bit more here. We had picked the x's to go from 0 to 4 and the y's to go from 0 to 20. But when we look at the graph of the inverse, we need to swap the domain and the range. So I'm going to recognize that 0 to 20 is good for the y's, so I'm going to change that 0 to 20 up here for the x's too. It's not going to be so great for one of the curves, but at least it should bring the other curve into the picture. Okay, and do we see any kind of symmetry here happening or any kind of reflection stuff happening here? Okay, so I paused the video because it was really hard to see the kind of symmetry that I was looking for. And what I've done is I've gone ahead and graphed one more thing here. We just graphed this guy plus. We're also going to graph this guy minus. So you can see the only difference is there, and the rest of it is on the next line. And when I graphed that, I got this guy right here in the top. And so this was the part that we had seen before, and then this is the rest of it. So now we're starting to see the kind of reflection symmetry that we were expecting. So there's the ball going up and down, and then reflect that guy over this diagonal line, and we get this kind of sideways parabola looking thing. It's not quite a parabola, but looks pretty close. I guess it is a sideways parabola. And so I like the symmetry that I see here, and I picked this guy, this second part, the 2 to 4 part. So which part does that correspond to? Is that the top part or the bottom part? Well, let's see. I'm just going to pick, for example, this point right here. If I flip it over the line y equals x, I land roughly here. So that's on the top part. I definitely don't go over here. These guys close to the x-axis must have come from these guys close to the y-axis. So the left-hand part corresponds to the bottom part, which somehow was the plus, and then the right-hand part corresponds to the top part, which surprisingly is the minus. And so the last little detail here, I won't even write it, it's written out in the answer key, but the little detail says that if we're going to choose 2 to 4, then we need to pick the correct part of this parabola right here, which was the top part, which surprisingly is the minus. And if we had picked 0 to 2 for the original, then we wanted to pick the bottom part, which is the plus. That's the same kind of little nitty-gritty detail that I said don't worry about it here. So you didn't worry about it here. I want you to continue to not worry about it. This problem is tough enough as it is. But anyway, technically we need to pick the correct one, plus or minus, based on the choice that we made up here. Okay, and then finally, mercifully, the last one, number 7. Let f of x equal x cubed, g of x equal ln of x. Find equations for f inverse and g inverse. Okay, so we can do that first. F inverse of x, you can go through the process, but this one is easy enough. What's the opposite of cubing something? Is taking a cube root of it. And then g inverse of x. What's the opposite of ln of x? It's e to the x. We know that's the inverse. Part B, let h of x equal g of f of x. Find equations for h of x and h inverse of x. Okay, let's try that here. So h of x first. Okay, definition says it's g of f. We'll go inside to the outside. So I'm just going to put here in the parentheses the f function, which is, where's the f function? It's x cubed. And then g inverse, and then g of x cubed is just ln of the thing in the parentheses, x cubed. So that right there is the function for h of x. Okay, fair enough. Then we want the equation for h inverse of x. So let's see if we can do this. Now that we've got h, we can find h inverse. So I'm just going to copy this guy. I'm going to call it y equals ln of x cubed. Just swapping out the h of x and calling it a y. That's our first step. Then we'll interchange the x and the y. And then solve for y. Definition of this guy, you can imagine the invisible e that's there. We'll follow the football pattern. E raised to that guy equals the thing in the parentheses. So we'll write that. E raised to the x equals the thing in the parentheses. Trying to solve for y, so cube root of both sides. And then last step is to use good notation, so cube root of e to the x, and that's f inverse of x. Except it wasn't called f, it was h in this problem. So that right there is h inverse of x, the cube root of e to the x. Okay, and then part C, how is h inverse of x related to f inverse and g inverse? Would this be true for any composition? Well, let's see. We just have to compare some stuff now. So we're looking at the cube root of e to the x, and we're trying to somehow find a relationship between that and these two functions over here, cube root of x and e to the x. Well, the function in green is actually the composition. It's the two yellow ones put together, and we got to put them together in the correct order. So let's say that the correct order here, let's see, we know that h inverse is over there in green. And green says the e to the x has to be on the inside. So if I'm thinking about the yellow functions, which one needs to be inside? E to the x, that's g inverse. So the inside over here is g inverse. And what is it inside? It is inside of f inverse. And you can verify that. You should verify that. Make sure that when you compose and you do f inverse of g inverse, these two functions here, that you actually do get this guy, cube root of e to the x. And so what happened here? Let's see. H was originally defined as g of f. H inverse became f inverse of g inverse. Not only did we have to invert the two functions, but what else did we have to do? We had to swap the order. Would this be true for any composition? It turns out it is. You just have to find the inverses of your two original functions and then compose them, but compose them in the opposite order that they were composed in before. This original order was g of f, the opposite order down here, f of g, but inverses on both of them. Turns out that's true all the time. Okay, I said in the class video that this was a monster group activity, or monster activity, I should say, and it was. It's quite a bit more involved than the class notes themselves, but hopefully you spent a lot of effort and time working through them, and whether you did or didn't, I would encourage you to look through them again and make sure that these concepts are solid.